Hello! In this episode of Finno-Ugric machining, it will be the cylinder for this rotating vane compressor. So, it's a lot of metal removal, some setup difficulties, etc. First of all, metal removal, and this will happen in the lathe. So that's where we head now. Yeah, okay. Yep, this here is my Bison 4-jaw chuck, independent jaws, 250 millimeters in diameter. Well, some might say that it's a little bit, big for this lathe, but it's not actually. It's very suitable, for example, for this workpiece. So I have dialed this in. It's within 200 of a millimeter in each direction. Why 200? Because this surface is it's not round. There is some deviation on it. Not a lot, but there is some. So now, of course, we need to face it. I think we have. Let's see about the. Okay. It's a half a millimeter deviation there. Well, it's too much. Oh man, I need to loosen these, I think, and put some copper under there. And one more. A little bit like that. Okay, now let's tie them evenly and start knocking it straight. Three-hundredths of a millimeter at the moment. Low, high. Straight. So now we go back here. This is the normal way of doing this. And well, there is a bump in this one. Okay, let's see. This is now low. This is high, but just a little bit high. Let's see. This is that. This is that. That's different. So that under one, this and that, all those three are the same, exactly the same. And this is different. It's like down. And now if I go here, that's high. Oh, it went all really crazy. That's now high. Okay, now it's okay. Then go back. It's still okay, good. And now retighten these again. That's tight. That's tight. That's tight. And the final one is tight. Well, it's straight. Both ends are really straight, and yeah, it's currently dialed in. It's concentric and straight. Well, the next step will be to have a hole through, and well, it will be as large as 50 millimeters. So it only leaves 10 millimeters at the sides. Well, I don't do the drilling here. I have a better machine for that. But I will make the start hole here. It's just center drilling this and then going on from there. And we shall go on with this hole in the drill press. Well, this boring bar setup, it fulfills the criteria of flimsy setup. Well, yeah. Well, it will whistle. I'm pretty sure of that. It shatters. But why this? I have a bigger one, but this hole needs to be well about 2 millimeters larger so that it fits in. Yeah, hopefully we can deal with this this thing. I'm going to peel off very thin layers from here and trying to, well, this insert what I'm using is very sharp and the cutting forces are very low. I have also placed it a little bit above the center so that so that it doesn't like dig into the material when it flexes. So there should be negative feedback here. But let's see. So, only time will tell whether this can be done. And when I start it, you can immediately see that this hole is not in the center. It's everything but. So let's start with this. Well, yeah. Oh, man. Oh. That went, well, not a lot of chatter, but the surface finish inside there is not good. It's because this, well, it vibrates, even though it doesn't make a real sound that you can hear, it really vibrates. And so we have recorded the vibrations into that surface. So this is a good boring bar, but not to be hanging like that. Okay, now I think we can fit the real thing into there. And the real thing is this. Oh. There you are. Let's see. And oh yeah, this is left-handed, so we turn it this way. Oh. Let's see now. Okay. Oh, it makes a very nice looking surface there. And of course the feed direction has now changed. So let's try half a millimeter first and see how it reacts on that. Well, okay, good. I'll check that this stop is correct. It is. Well, even this is flexing quite a lot, and the surface is, well, it's not good, but it's better than the previous. And we have a lot of chips in there. Maybe vacuum them. Let's look into the it's filled with chips. That gap. Let's see if this works. If that works. Okay. Let's see. Now it's 1 millimeter cut. It's half millimeters now. Doesn't break the chip yet. It changes to 1 millimeter very soon. Now. Yep. It's breaking the chips. Good. There you are. Well, the surface is not good. So, at the moment this is 49, it's 45 millimeters at the moment, roughly. And, well, we are going to go up to 49 with this insert, which is producing very bad surface here. It's not usable for this task. so I need to make it a lot better. And then the chip evacuation works in a way that it will be making a very long chip which is coming out from the backside of the lathe. Well, it's okay for me. It's okay when it comes out. Sometimes they collect here in the back, and then I stop and take them out, and then after that just go on. Well, the speed is 300 RPM, and the feed is 0.076 millimeters per revolution, and the cutoff depth is 1 millimeter from diameter, so 0.5 millimeters each side. So yeah, so let's go on. We have 4 more to go to be at 49. Okay, now this is the last millimeter with this boring bar. It has warmed up a little bit, so I need to let it cool down before I continue with the surface finish, because that also determines the final diameter. Uh, well, I lied you about the feeder rate. It's actually 0.152 millimeters per revolution, not 0.078 as I said earlier. That makes the ships a little bit more manageable, and they come out from the backside of the lathe, and as you could see, sometimes they make a blockade here, so I need to clean them up and then go on with the boring operation, and of course the surface finish is really bad. But this will be sorted out pretty soon. Well, okay, I already peeled off the rough surface, and the finish is at the moment, well, it's acceptable. It will become better once I now make another round, because it inherits some of the surface features when it, because this is quite flexible. So it sort of plays the surface finish there. And but this pass is, I will make now another pass, 0.1 millimeters, and with cutting oil. Like that. The speed is about 150 revolutions per minute, and the feed is very slow. It's 0.038 millimeters per revolution, and now I'm dialing in 0.1 millimeter cut here, and after this I will measure it. Well, yeah, so let's go. Well, this is now the final spring bath. You shouldn't do this, but I decided to. I didn't adjust the diameter at all. I just now run it like against the cutting surface of the blade. And this insert has a very tiny rounding radius, and now that radius is working at the moment. It's taking care of the surface irregularities there, and I can already see that it produces, well, a super finish. And furthermore, because I'm feeding this now to a different direction, it creates a crisscross pattern there. This should yield a very, very good surface finish. But, well, I already checked it. I stopped it a little bit and checked this by my finger, and it looks all right. Well, and this is extremely slow process. If you think about it, we are running 150 revolutions per minute, and we are feeding 0.038 millimeters per revolution. I will do the calculation here in the video so we can see how long time it takes for one pass with this setup. And I really don't know what the cutting depth is. It's might be 300s maybe. It's very small. But I still don't want to run this very fast because this might chatter. So yeah. And one more thing. When I was doing the last passes the other way around, I noticed that if I cut only 0.1 millimeter from the diameter, it will chatter. So it must be, in this case, it must be at least 0.2 millimeters. Then it stops chattering and produces a better surface. Well, but it was still, because this is so flimsy, this boring bar, it produced, bumpy. But this one now seems to produce a very nice, smooth, even surface. So, let's just let this run. Yeah. So, we finalized this surface here, and it's really smooth. And the diameter is 300ths of a millimeter undersize. Well, it's okay. I can live with that. Oversize as well. I just need, when I do the rotor, I need to take in account that small thing. Now, the final step before we can get this part out of the chuck is to level this surface so that it is absolutely perpendicular with the bore. So, I'm using this insert. It's in a little bit of an angle here now. And I will be running this a little bit faster, something like 600 maybe revolutions per minute, like that. And it should. It should. I don't take a lot from that. I only take about 5/100 of a millimeter at first. Huh? There you go. So this is just 5/100 of a millimeter. There you are. And the surface is like not mirror, but it's very, very even. Okay, I took it off from the chuck. And then I measured it, and then I dialed it in again. We need to take off 0.32 millimeters from this surface. I will do this in two passes. First pass will of course be 0.15 millimeters. Well, that surface is really nice. It's definitely flat, and yeah. So now I take it out and well, I measure it. Let's see what it will be. I believe it's well, maybe 1 or 2 hundredths of a millimeter oversize. It should be. Oh, well, yeah, so we have a cylinder. And this one is now it needs 8 holes each side. And those must be perfectly aligned with each other. But that is a milling operation. and it will be in the next episode of Finno-Ugric machining. But what I did out of the camera, I noticed when I did measures from this side to side from different places, I noticed that these were not parallel. They were, well, as much as 400ths of a millimeter out of parallel. So I put this thing again, dialed it in each side, because I didn't know which side was tilted. Maybe both. And then I did this with copper pieces on the jaws so that I could be knocking it really exactly. And now they are parallel, well, within 200ths of a millimeter. Well, maybe more accurate than that. But as a consequence, this is now 500ths of a millimeter undersize. It just means that I need to do all the parts that go inside there undersize as well. Well, such is life. Well, we will be continuing with that cylinder in the next episode of Finno-Ugric machining. Hope to see you then. So, till then, bye!